on analog or mixed VLSI circuits for brain-machine interface, organized by the Department of Electronics and Communication Engineering, National Institute of Technology Silchar. We have with us for the afternoon session Mr. Saurav Nath from NIT Silchar. He did his BTech from Sikkim Manipal Institute of Technology in the year 2011. He is currently working as VLSI lab engineer under SMDP2 and SMDP C2SD in NIT Silchar from 2012 till date. He has completed his MTech from NIT Silchar in the year 2020. He is a doctoral research scholar in the Department of ECE NIT Silchar. His area of interest is VLSI circuit design and optimization. His area of expertise is analog application-specific integrated circuit design flow. I'd like to request Mr. Saurav Nath to start his session.
Thank you, Banani.
Thank you, sir.
It's nice introduction. Actually, I am here to present or share my experience regarding the chip tape-out process, which I have encountered in the design procedure during my project. So basically, this is a long journey, but I have summarized in a brief manner so that we can complete or show the things in this stipulated time. So these are the outlines I'll be discussing about this Moore's law. So everybody knows about Moore's law. So VLSI, being a VLSI guy, we should know Moore's law. Technology nodes, what are the available technology nodes, and then VLSI design style, ASIC design flow, front-end analysis and simulation. I'll be talking about some analysis, layout basics with reference to SCL180nm PDK, and then tape-out process followed by conclusions. So Moore's law, it states that in every 2 years that number of transistor per chip is doubled. So in today's area scenario, the time is shrunk to 18 months even. So latest processor up to Intel Core i7 is also here. You can see 10 to the 9 number of transistor is using. I have shown here from starting from 4004 to a latest processor even. So these are the technology nodes. We have to know about technology nodes. So what's the available technology nodes? Because if when we will be designing the circuit, we should know about the minimum channel length of the transistor which we will be using. So, and these are the available technology nodes starting from 180nm technology. I have shown here up to 5 to 3nm technology, which is in research. AMD Ryzen processor is using 7nm technology, and Intel latest processor is also using 14nm technology. So these are the available technology nodes, and how the technology node is decreasing, it follows that pattern, that is 1/√2 times the previous technology nodes. So this is all about the technology nodes. So we'll be using here 180nm technology for the demo purpose. So next is our VLSI design style. So there's a 3 major design styles which we'll be following during our design. Basically, full custom based design, semi-custom based design, and standard cell based design. In full custom based design, everything is designed handcrafted. So required high design time, and design is highly optimized, but it requires high design time. Mostly using analog IC design. You can design from the scratch. Every layer by layer you can design. And in semi-custom based design, they generally mixed signal based design is followed by semi-custom based design, where the foundry file is required. From foundry file, layout file is taken, and transistor symbol is taken, and accordingly the schematic design is done. And from that schematic, layout is generated. So it requires moderate design time, but less than the full custom based design. So we will be showing here semi-custom based design in this demo. And in case of standard cell based design, the layout height is fixed, and it is done through scripting, required less design time, because in digital IC design there is lots of transistor use, so you cannot design each and every transistor by your own hand. So it requires some automation based or scripting based language so that you can generate the netlist file, and corresponding layout has been done. So this is the process of standard cell based design, and in most of the industries nowadays using standard cell based design because it requires less design to market, time to market. And this is ASIC design flow. So before going to the process, practically we should know what are the basic steps required for designing a circuit or designing an ASIC, both in digital domain and analog domain. Actually, the design is divided in two groups. One is for front-end design, and other is back-end design. Now, in analog design flow, after getting the specification, if you consider analog design flow, if you after getting the specification, schematic design entry is done, and after that followed by analog simulation, that is analog design environment. Here ADL is the version of the simulation analog design environment, and corresponding the output is checked. So if the output is up to the mark, then layout is generated depending upon the schematic, and followed by DRC, LBS, and PEX. That is the verification steps is done. In case of digital design flow, after getting the specification, Verilog coding is be done. Verilog or VHDL coding, any HDL coding actually is done, and behavioral simulation is done. So after getting the output, if output is matched, then proceed forward for Verilog synthesis with a particular technology node, where we can add our required technology files, foundry files. That is actually here required on the technology DB file, database file is required, and lib file is required for synthesizing the Verilog code according to your design. After that, post synthesis simulation is done, or LEC. After synthesis, logical equivalency check. Logical equivalency check is done. Logical equivalency check is done, and if for getting the confirmation of Verilog coding along with the synthesis netlist, whether it is one-to-one mapping or not, that is done. After that, in case of analog, post layout simulation is done. If met, layout with IO pad for chip tapeout processes will be carried forward. After that, full chip design verification and simulation is done. In case of digital, timing analysis will be carried forward. After that, if timing is met, then we proceed forward the physical design, where floor planning, placement, and routing will be done. After that, a post PNR LEC will be done, to check whether after routing is anything problematic or not in the design with our reference design. So if met, then GDS2 file is extracted for fabrication. It is a graphics database system information interchange file, which is required for fabrication is generated. So these are the tools which we will be using in our design flow, or which we are actually using in our lab. From Cadence, we are using a schematic editor for analog design, ADL, and under multimode simulator engine is used. Under multimode simulator, there are lots of simulators there: Spectra, ASPICE, UltraSim, AMS. Depending upon the design complexity, Spectra, ASPICE, UltraSim, and AMS selected. Actually, AMS is used for analog mixed mode simulation. And after that, the backend design is done using Virtuoso layout editor. Another tool is for digital design. Innova's tool is used for digital backend design, where for VLSI physical design is done in this tool. And in farm synthesis, we are using Design Vision tool for Verilog netlists and generating Verilog netlist. Time is used for timing analysis. Vardy is used for Verilog code simulation. And from Mentor, one popular tool, Caliber tool, is used for design verification. DRC, LBS, and parasitic extraction is done using Mentor tool, Caliber. So these are the three industry-oriented tools we are using in our lab for doing these sorts of works. So let's come to the analog design, circuit design. How a circuit design is approached, or how a big circuit design or any analog circuit can be approached with the things. What are the things required? First of all, large signal analysis is done by getting the system design specification, and objective function is realized. Objective function here means if you use a soft computing algorithm to optimize your output, then an objective function is required to generate or realize. After that, a soft computing algorithm will be attached with this objective function, and corresponding the W by L ratio or load capacitance, anything, any parameter is find out using the soft compounding algorithm. We are using PSO, human behavior PSO. There are lots of algorithms, swarm based algorithm we are using for determining the values of W by L and load capacitance or anything, any parameter if you require. Finally, the aspect ratio, after getting from the soft compounding algorithm, that is from MATLAB, we actually put in the cadence simulator, and design is verified with that values, and corresponding optimized output is determined. So this is the common flow. This is the flow we are following in our lab to design analog circuits, basically. So these are the software requirements for circuit slicing. Actually, this MATLAB objective function is written in MATLAB. Here sample objective function I have told. This is the inverter fault time optimization. This VDD and BTN values are taken from the foundry. KN is also taken from foundry. That's V1 CX value, and this is the expression for fault time. Actually, only the WL ratio of NMOS is required for fault time and load capacitance. So this is the expression written in MATLAB. Accordingly, some algorithm will be attached with this function, giving the design constraint, and the corresponding values is obtained as a aspect ratio of transistor or other parameter. And this value is fed to the cadence, and we can get the result output. So this is the software requirement along with the process I have shown here pictorially. Now these are some analysis which will be carried forward in Frontend. That is mainly 3 types of analysis will be carried forward in analog design. Will be carried forwarding: DC analysis, AC analysis, and transient analysis. Under DC analysis, we will be doing DC operating points check, whether the transistor region, determining the transistor region where the transistor falls with biasing. ICMR input command mode range test, and DC characteristics plot. If any DC characteristic plot is required, then we go for DC analysis. DC node voltage and current determination using DC analysis we can do. Static power calculation we can do using DC analysis. DC offset calculation, so we can do for DC analysis. With this DC analysis is over. Next, AC analysis. Under AC analysis, we basically check gain and phase, CMRR, PSRR. CMRR common mode rejection ratio, that is differential gain minus common mode gain, we will do. PSRR, power supply rejection ratio, where we will find if any noise component, how much noise component is rejected from the power supply. So this is an important parameter for us op-amp based design. Under transient analysis, we will find slew rate, dynamic power, and transient response of the circuit. So these are the 3 analysis, method analysis we will be carried forward in analog design demo. And if you design in analog, any analog circuit, you have to follow these 3 analysis. So these are the setup for ICMR, where you can see that I have chosen an op-amp based design, 2-stage op-amp based design, where B in is given to the non-inverting input, and inverting input is shorted to the output, and corresponding the output is taken from common mode current versus input voltage. That is, this is the curve we will be obtained, and this from this we can determine the range of the input common mode range we can obtain here. So this will be the plot. Next, PSRR setup. If you want to find the power supply rejection ratio setup, then this will be the setup. If you have to short the non-inverting terminal to ground, inverting terminal shorted to the ground, and we have to give some SC magnitude to the power supply. It is BSS or BDD. We should introduce some SC small signal voltage as a noise component, and perform the analysis as perform the SC analysis, and get the plot of BDD versus B out or BSS versus B out to get this type of plot. And we can if the gain is maximum, then the rejection is also maximum. In this way you can interpret. This is a CMRR setup, where the 10 millivolt voltage SC magnitude given to the non-inverting input, and in inverting input I have given a variable X. For first of all, we will do analysis by keeping the value of X as 0. After that, we will plot the gain. This gain will be our differential mode gain, and then another analysis will be done by keeping the value X value equal to the V in plus value, and we will get the common mode voltage. After that, in calculator, we will subtract this AC minus AD minus AC, and we get the similar plot. So here in this graph, it will be much more clear. This is the common mode gain, and this is the green one is the differential mode gain, and this red one is the CMRR. AD minus AC I have done in using calculator. So this will be our CMRR plot. Another DC offset calculation. DC offset calculation giving a 0 volt DC in the non-inverting terminal, and inverting terminal is this shorted to the output. So now vary the input voltage and check the values at the output. So this will be give the systematic offset, and for random offset of system, you have to carry out the multi-color analysis by vary the V in from minus 1.8 to plus 1.8, and corresponding output is taken as from the histogram plot, and standard deviation noted from the histogram plot of a multi-color analysis. For folded crossover topology, inverting and non-inverting must be strictly identified, and inverting terminal must be connected to the output. Otherwise, there will be some problem in the output, or maybe it's either output. There will be an error. Next, this will be our slew rate test, where I have given a pulse or any sine wave sensitive input at the non-inverting terminal, and the inverting terminal is shorted to the output, and corresponding the output is taken from V out, and by pressing A and D at the output waveform, we will get the slope of the waveform, and corresponding slope will be the slew rate of that waveform. So this is the plot. You can see here, this is the negative slew rate. A and D is pressed starting from 90% to 10%, and this is the positive slew rate, 90%, and after that you are getting the slope here S. There another slope will be there. So after taking this average of these two slopes, we will be getting the slew rate of the op amp. So now next is the static power analysis. Static power test means we can do it through DC analysis, and under ADL there is an option called save output. In output, under output there is option called save all. So you have to check all this all and then run the analysis. After running the analysis, open the result browser and check the DC op, and you will get a power output in the signal tab. So this will be the static power of the circuit. And dynamic power, the setup is same. Only we have to do transient analysis, and corresponding output will be taken from the result browser from tran. In the pane, there is an option called tran, and a power signal will be there below the tran, and the output is formed by clicking the power signal, and you can see the output in microwatt or milliwatt, whichever depending upon your circuit design. So this is the dynamic power output. Now let's move to a demo of this analysis, so that it will be much more understanding, and it will be clear for you. So let's start the cadence. Now here I have opened the cadence. This is the cadence console. I am using IC 617 64-bit version, and it's the library manager. So for designing a new circuit, we have to make one library. For that, go to File, Library. So let's design an inverter for simplicity. Now we have to attach one technology library. So I am using SCL180nm technology. This will be my reference technology. So here there will be inverter, Yes, the inverter underscore total. A blank library is created. So after that, go to File, New, Cell View. A schematic inverter should be designed. So this is our schematic editor. So press I for generating any instance. Browse from your reference library.
Hello.
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 Sir, your screen is not visible.
Yeah, it's visible. I
Your
have
screen
already.
is not visible.
Yeah. My actually, I have verified with other user also. It's visible. I think. You can check it. Which hello. 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 Is it visible? My screen is visible. Okay.
Sort of it's visible for us. I think
Okay.
Mr.
That's problem.
Tarun Kumar, you can check your network connection once.
Mm-hmm.
Rejoin once again, then probably it will resume.
Yeah. So from SCL 180 nm, you have to check for NMOS and PMOS. For inverter, I require NMOS and PMOS. So one NMOS and one PMOS. So this is the PMOS I have given here. I'm just changing the name as N. Now just test W for connecting the wires or wiring. Here the PMOS body should be connected to VDD and MOS body should be connected to ground. This is the norms of SCL. So connect a pin here by pressing this VDD, GND, input, press R to rotate. And there another pin should be there, input. So this will be our output. Out. Check and save. After designing anything, you have to say plus check and save to generate the netlist or alter the netlist. So this is the main design of my inverter. This where should be deleted. Check and save. Now let us create one symbol of that. So create cell view from cell view. So let us put the ground pin at the bottom and VDD pin at the top and press OK. So this is the symbol of the generated by default symbol generated. So you can also alter this symbol as your inverter symbol. You can delete this. You can delete this. You can also delete this and press L. This wire. And join this. Now one bubble should be there. So you should keep one bubble here. can keep it also here, but still for better looking you can set the thing accurately. Where is it? Keep the instance name close to the design. Check and save. So this is the symbol I have made. Now close it. Now under this same library, make one test bench for testing or analysis, doing analysis. So inverter TV. TV. New cell. Press I and go to your generated library. From here you can also go to your drop down menu, inverter, inverter at all, inverter. This symbol is coming. So this is the inverter symbol I have called, and accordingly I will keep on instantiating the required DC voltages, other thing from analog library. DC 1.8 volt L maximum. Ground. PDD. And connect with this. Copy this. By pressing C, you can copy. Now, a port should be there. Out. Here I have connected DC voltage source at the input. So I will do DC analysis and check the DC output characteristics of inverter. So for that I have to go to ADL. I have already told in the slide ADL. Now I have to do the setup for giving the model file library. Model libraries, go to model setup, model libraries. You have to give the model files of SCL. Here under model file, there are lots of section. This section is given by the foundry. TT means typical, SS means slow, both NMOS and PMOS are slow, and FF means fast. FS means if PMOS is slow, faster, then NMOS will be slow. Then if PMOS is slow, then NMOS will be fast. SF. Lots of sections are there. These will be given by the foundry. So for the demo purpose, I am selecting the typical type. These are the corner actually. Choose DC component parameter. Then select this component. I will vary this component. Which component? This component. Which parameter? DC parameter. I will be varying. Next, starting from 0 to 1.8 volt, I will vary the input voltage to see the characteristics. Next, click on run button, play button. So it will So I have not given any output, so you can select design on this output and this input, and then again run it. So this is the, you can see here this transfer characteristics of inverter. You can see here in up to this the inverter is taking as a low input. After this it's taking as high input. So this is transfer curve we have obtained. And now let's do transient analysis. So click disable on this DC analysis. Then you have to give transient source. To cancel previous command, press escape. So give B pulse. So let us configure this pulse. Maximum voltage is 1.8. Period say you 200 nano. Price time typical 10 pico. Fall time say 10 pico. Pulse width half of the period to maintain 50% duty cycle of the pulse. They can save. Now for transient analysis, one capacitor also required. For that, check the rise and fall time. Cap. So by default 1 pico. Let us increase this value to 5 pico. So check and save. Now go to ADL, analysis, choose tran. Under tran, give the stop time, which should be greater than the period. So 500 nano. These are the modes of 3 modes of simulation. Conservative means mode resolution. There will be mode resolution. Moderate means medium resolution, and liberal means less resolution. So if the design complexity is high, then we prefer liberal simulation. If the design complexity is medium, then we prefer moderate. And if the design complexity is less, then we prefer conservative to get the best output. So run it. So due to the capacitance, the output is deteriorated as rise time, fall time is there. Charging, discharging path is there in the capacitance. So now if you change the value of capacitance, change the value by changing the value, press Q, properties, suppose 1 picofarad. So what will be the change in the output? You can check. So and there's more good output. You can see here. Less fall time is there, less rest time is there as before. So this is the transient analysis. We can check the rise time and fall time by using calculator also, and also by giving the 90% 10% time difference by calculating the 90% and 10% time difference, rise time or fall time. So this is all about the transient and the DC analysis of an inverter. Now let us check the analysis of a op-amp, which will be much more beneficial for analog designer. So this is a op-amp, SCL180nm 2-stage op-amp. A test bench is there. So if you check the circuit, here it is the circuit I have already designed. So let us simulate it. First of all, we will do SC analysis to check the gain and phase value of the op-amp. Go to ADL session. Let's check the setup. Yes, model library is given here. Extra model library is used mimcap type. Actually, I have used the capacitor from SCL. So from SCL library I have to give, and correspondingly section of this model file is selected as mimcap type. Typical mimcap as a typical. So run it. 3 analysis will be done: SC, tran, and DC analysis. Transient. So let's check the result. For result, go to result, direct plot, SC gain and phase. You have to give the B out versus B in. So this is the green one is the phase plot, and this orange one is the orange step. This one is the gain plot. So 17 dB.7 dB is obtained here. Accordingly, from this plot we can measure the phase margin, gain margin, cutoff frequency, 3 dB bandwidth. Everything can be determined by using the cursor or marker button. So for marker, horizontal marker, you can place H. You can place here up to after minusing the 3 dB. How much? 17.7. So around 14.7 dB. You can have to. You can check the 3 dB. 14.6. Suppose this one. So this one is the 1.9 megahertz is the cutoff frequency, 3 dB bandwidth of this amplifier. So in this way, lots of parameter can be obtained from this analysis, from the waveform itself. So now let us check the CMRR plot, which is most important. Here in this reference voltage, you can give X a variable. So under this, you will copy from cell view. So there will be variable. First of all, go for 0 voltage. Oh, I have not given check and save. This is much more important. I have altered the parameter and I have not given the check and save button. So this is one differential again, which is already obtained earlier, which is already shown earlier. Now let us make it same as the input 100 micro AC magnitude. Just check it whether some deflection is giving or not. So this is minus 33.5 dB, which is a common mode gain. So we have to get the difference between AD and SC. So after that, you will get the same error using calculator. So for that, you can go to tools, parametric analysis, select the variable X starting from 0 to 100 micro, only 2 steps, then run button. So at a time there will be 2 simulation of both common mode and differential mode. So close it, go to result, direct plot, gain and phase, A out by B in. So these are the plots both for common mode gain and differential mode gain. Now from this waveform, let us delete this phase plot. Now let us make a difference between this one so that we can get the CMRR. So go to calculator. This is the waveform. Select the waveform button. Click on this green one. Minus, this is AD. Now copy this value and again go to this one. Click on there, Control V, and then plot. So this blue color is the 51.34 is the CMRR plot. CMRR plot we can obtain from this analysis. Common mode reduction plot. So this is all about CMRR plot and SA analysis of op-amp. Next, let us do transient analysis. For transient, I have given one sinusoidal input with a frequency of 10K, 100 microvolt in amplitude, and 10K frequency is given. So let's disable the ASIC, or you can keep it as it is. So a transient analysis is done. Now let's observe the result. Go to tools, result browser. Here, go to tran. So this PWR is the power output. Here I can see 194 average, on an average 194 microwatt is the power of this circuit, dynamic power of the circuit. Now under DC op tab, you can check another power. This one is the static power, almost same. By doing DC analysis, we can check it. So I have already given the DC analysis in the ADL window. So it's giving the power 194 microwatt, 0.5 microwatt. And from here, this power can be taken, this power is again taken average, so that accurate power can be obtained. So let me take this power, and another function is there, average, average, then calculate. So 194.5 microwatt is showing here. So this is the average dynamic power. So this is all about transient analysis. And you can also check the slew rate also. Result, output, plotted, select and design. Transient response, from transient response you can check. So here this is the transient response of the output amplifier. And if for checking the slew rate, you have to press A by pointing anywhere at around 90% or 10% difference D. So slope is here. You can see 43.20 volt per second is the slew rate of this amplifier. You can also check this is a negative slew rate. You can check also positive for using indicating in the for stem A and D. So two slope is there. So the new slope will be the positive one. So taking the average of this positive and negative slope, we can check. We can determine the slew rate. You can also use calculator. There is a function called slew rate, so you can also use that. Slew rate. There is a function called slew rate. So you can also use this signal final value, initial value, so that you can calculate the slew rate. It will be almost same. So I have shown two method of calculating the slew rate. Using one is using calculator, one is directly from waveform. So let this all about the front-end analysis. Rest of the analysis will be if anyone requires, and contact me. I will provide the data of rest, because there's a time constraint. I have to go to up to chip tapeout, so it will get lots of time. So remaining analysis, if anyone requires, then please contact me personally. So let's go to again the presentation and check some basics of layout. So demo is over. So now let's talk about some layout basics. Actually, we are using the CMOS technology. So this is the basic CMOS structure, NMOS and PMOS, where there is a P substrate and there is an well for well required for making PMOS. And in SCL180nm technology, we are using one via called M1 P active via for connecting the body to the substrate. And for PMOS, we are using an M1 N active via for connecting the body to the N well. So in case of NMOS, source and body is shorted. It is grounded and is in case of PMOS, it should be shorted to the VDD to reduce body effect. Actually, this is the norms of SCL180nm. If you follow the UMC PDK, then you can short only source body shorting is enough. For every transistor, you can short the source and body. But for SCL, they have told us to maintain this. And if PMOS body biasing is required, then connect it to VDD. And if NMOS is body bias is required, then connect it to ground. So this is the norms we are following in the SCL PDK. This is this picture will give you more clear. This is the PMOS, NMOS via for body biasing. You can see I have mapped 1-to-1 layer, and the source body I have marked it with the color. You can see this pink one is the N well, and this is the N1 P active, M1 N active via for connecting the via of body of PMOS. So this is the basics of layout. We can we will be will be shown in the we'll be showing you in the layout demo. So this is the sample layout where you can see I have connected shorted the body to the PMOS. Source body shortage is there, but SL is not maintaining this, so we have to alter it, and we have to connect the VDD to the body of the PMOS. And this is the some sample NMOS PMOS connection I have shown in the layout. I'll be showing in detail in the layout demo. This one, another one is called PM1 poly via, used for connecting the polysilicon to the metal. And so after designing the layout, the next step is the design verification step. So these steps actually it is done by a mental graphics tool called Caliber. Under Caliber, we will be doing a design rule check, DRC. Here, micron based design rule is used, and layout versus schematic is done, LVS, and parasitic is done using this Caliber tool, mentor tool. So and after designing, after verification, post layout simulation will be done. Post layout simulation basically done using generating test bench with two instances of your design, giving a same input to the both the instances, and create a config view with hierarchy editor in Cadence, and after that carry all the analysis in config view. So this is one process. Actually, I will be showing here in another shortcut method for doing post layout simulation, which will be much more easier than these steps. This is the normal process of followed in UMC when this is a normal procedure. But it's due to shortage, you can use a shortcut method. So I will be showing in this demo. After that, post layout simulation is done. You have to you have to go to pad frame designing task. You have to design your pad frame with IO pads. There is two way to design your IO pad. One is manually you have to instantiate the IO pad layout view in your layout editor window and connect it accordingly, one by one. This is much more tedious, and that's why I have marked this block as red. And another way is automating pad frame generation using Verilog scripting in Cadence Innovus. So you can generate a Verilog code, an netlist code, and you can run it in Cadence Innovus, and it will automatically generate the pad frame ring according to your desired specification. So this is one way. I will be showing this automatic pad frame generation using Verilog scripting in Cadence Innovus. For the demo purpose, the IO pad I have used PC3D000. For this is a normal common analog IO pad, and for power pad PBDA port PB0i and PBDA and PB0a. PBDA and PB0a pad is used for the powering the ring, pad frame ring are used. There are lots of IO pads, but you can use any one of them. It comes with the document given by the foundry, so you can choose depending upon your necessity and specification whichever required. So next, so this will be the final outcome after doing the layout. After doing a pad frame generation, you have to give you a layout, and here you can see this is a silicon number that will be provided by a foundry for fabrication, and this green border is called seal ring. And these are the IO pads, and middle there is a filler called IO pad filler is there. In between IO pad there is a filler, so we have to get the power from this filler, and all IO pads should be powered. For that, PBD0A and PBDA is used. Pad is used for powering this ring, and these are called corner cells. Corner cell, and under the ring it is called core area. So this is all about. So after you have to design your layout up to this level. After that, bond pad diagram is used. Bond pad diagram actually GDS file used to be requested from the foundry. They will provide the number of, depending upon number of pins, other specification, they will provide you the bond pad diagram GDS file. That GDS file should be imported in your Cadence Virtuoso, and your your complete chip tapeout should be under this bond pad, and the corresponding bond pad diagram is made using the top metal layer. This yellow color is the top metal of the SCL180nm technology, because top metal layer is used because resistivity will be low. So this connection is used for bond pad diagram, generating the bond pad diagram. So let us go to the demo of a backend design. That will be much more easier and clear for you, whatever I have told. Go to Linux again. I am going. So we have designed one inverter. So let us make this schematic. Open the schematic. So this is your inverter. Now for designing but being layout, we have to open the layout editor window. So for that, launch layout Excel, create new. Okay. So this is the layout editor window. So before instantiating or before generating the layout instances, we have to set the grid size. This dotted structure, this black dotted structure page is called a P substrate. So we have to say, set the values for these small grids. This highlighted dot is called major, and this is minor grids. So you have to check the resolution of this window. After that, we have to generate the layout view of these two transistors, and correspondingly wiring should be done. So for that, go to options, display. Here you can minor and major spacing. So for minor 0.005 is given by foundry, the grid size 0.5. XNAP should be same as minor. So this grid size is adjusted now. Now let us generate the layout from schematic. So no need to IO pins, PR boundary, only instances will be okay for us. That's okay. So this MOSFETs already inbooked as layout view. So for getting the layouts, press Shift F. So these are the two MOSFETs that are used in our schematic, PMOS and NMOS. Now let us make the connection. First of all, let us connect the gate. For gate, we need a polysilicon. This is polysilicon color. So search for GC. This is the name of polysilicon in SCL, GC. Drawing layer. Press R for rectangular drawing. Zoom it and select the source corner, and it will be guided by a fly lines. You can see here. I am being guided by the cadence. So this is somewhat for press S for stretching the layer. You can stretch the layer. So I have connected the gate here. Now let us connect the drain. For that, we have to select the metal. So metal 1, M1, select M1. So I have connected the gate output terminal. Now let us connect the VDD and ground. So I have connected the ground of NMOS. Now I am left with the body biasing part and input output terminal connection, terminal generation. So for body biasing, we require M1 N active via. So for that, as I search for this, where I can get M1 inactive. So you can see here I have kept no gap between this NVL and this via. This is required for NMOS, PMOS only. For NMOS, it's not required. You can tap anywhere between 30 micrometer. Now, let's connect the another via, P-active via for this. This anywhere you can place it here. Here also, here also, here you can also place here. So better to place here within 30 micrometer, because this is P substrate. Black one is a P substrate, so we have to short and a P substrate with this source. So that's all. Now let's connect M1 poly via. For via, press O. Press O for via M1 poly. Now connect M1. Check save. So my layout is over for this inverter. Now I have to label this terminal. For this, press L. So name it same as schematic, VDD, GND, in, out. Select layer, M1 label. Here is the label. Select it. You can change the font even. I prefer Roman. So this is VDD. You connect it here. VDD is there. Ground is there. In, out. So same. So I have done my labeling. Now it's time to check the DRC, LBS, and PACS using the mental graphics tool Caliber. So go to Caliber, run DRC. It will take some time. So it's coming. Press OK. So run DRC. All right. Okay. It's running. So these are the results, either some DC1, DC2, and 6W and 9X. So these we can ignore because this is related to the die, and for after designing the whole chip, this is automatically abolished due to some dummy layer problem that this series is coming. So layer density, some other problems are there. So you can check here the coverage area is less than 0.14 9x. The coverage area of M1 metal layer is less than 0.20 micron. So this is related to the density of metal, nothing related to the width and space. So I can ignore it for the time being. But during the submission of whole chip, full chip, we cannot ignore these types of errors. So we have to fix it and then generate the JDS file and send it to the foundry. So ERC is done. Next, we have to do LBS. For LBS, go to Caliber LBS. So LBS window will be invoking. So it's ready now. Run LBS. So its smiley is shown. So there is no error between layout versus schematic. So no problem. Then let us check the packs. Run packs. Packs run set. So create all terminals, schematic design. Press OK. You have to give the cellmap file here. Here cellmap file is given. Okay. With 0 warnings and 0 errors. So completed. Now close it. Here you can see another view is created. Caliber view. Caliber view is created. From this view, we will do post layout simulation. Using this view, you can see here capacitive capacitance and resistance is there, and pin is there, BDD, BR, everything is there. So with this generated view, we will be doing post layout simulation. So now close it. Close it. Now open this test bench schematic. Now we are doing post layout simulation. Launch ADL. Now one thing should be changed here. That is, go to setup, environment. Now here is a first view is there, spectra, CMOS. So you have to change it by putting a caliber view first. Reference caliber. This is a shortcut process of post layout. Otherwise, you have to make one config view. You have to take 2 instances of your design, make a separate test bench. Lots of things are there. So this is the shortcut process I am showing you by giving us caliber view in the environment options. The problem is there, I think. Okay, some corruption is there. Let's check the netlist first. So we have to generate caliber view again because some corruption is there. So let's delete the view. Unpacks. Zero warnings, zero errors. Now it's success going on. So it's showing the same output as previous because it's a small circuit, so there will not be any deviation with this parasitic generations and this is a low frequency, so no problem will be there. So if for RF circuit this deviation will be more, there will be more deviation for RF circuit because parasitic capacitance and resistance plays a vital role in the RF circuit. So this is all about the post-load simulation of inverter. Now let's move forward the chip tapeout process. Close it. Now for tapeout, I have made some file which I think you should check it out. This is the pet frame test Verilog file I have written. Here you can see a pet frame module is created with some input and output. You can give or you cannot give, that's optional. Input output is optional here. And here I have instantiated PC3. This is, as I have already told, but I have used this iPad and I have given a name 1, 2, 3, 4, 5, 6, 7, 8 up to 20 pins along with 4 power beds and corner cell. This is the name of corner cell. Corner cell. Yes, corner cells, and this is the iPad instantiation in the Verilog file. So with this Verilog file and another file is required, IO assignment file. This is required for placing the IO according to your position, for which IO pad is placed in which which sides and which pad is either in top or bottom or right, left, where should we place this IO pad, particular IO pad. You can make it in this IO assignment file.io file. Another thing, I have made a tickle file. Here, this is Innova's tickle file. Here I have given the LEF files, layout extraction format file of the IO pad along with the technology files, and corresponding the Verilog netlist file that I have shown. I have a pad frame i.io file and top cell name pad frame, and this is the dimension in floor plan. I have given the dimension 1328 micro, because I SCL give a minimum of die size of 2 mm cross 2 mm up to shielding. This is up to shielding. There should be 2 mm cross 2 mm. So I have make my core with 1328 micro by 1328 micro. With the core and IO spacing is 50 micro. Top, bottom, left, right. I have given 4 values. And other thing I have shown here, add ring version is there. We have to add power ring, VDD and BSS with top metal. Here I have seen top metal I have used, and the width of the assign in switch dash width is used to assign the width of the ring 10 micron. And this is the other parameters is used. Offset is there, so you can check it here. Another command I have used, add IO filler. So between the IO pad there should be a filler cell. So I have given all the filler cells and given a name filler IO, and fill any gap command is there. So there will be no gap between these fillers, and corresponding the GDS file extracted as pad frame ind pro.gds file. You can change it accordingly according to your name. So these are the files required for the automation of pad ring. Now let us check how pad ring can be automated. This is the Universe tool, and let's check the terminal of the Universe tool here. You can see. So as we have written the tickle file, so we have to just source it. Source pad.tickle file. So this is the pad ring generated in our Universe, as well as I have given all the command, all the commands. So for saving the GDS file, a GDS file is also extracted automatically. Here you can see this is the IO ring, BDD and BSS ring, and these are the IO pads, and in between these IO pads filler cell is there. So minimize it. So there you can see pad frame and ind pro GDS file is generated. So with this GDS file is again invoked and imported in the Virtuoso, and corresponding layout is done in the Virtuoso layout editor. Now let's import this GDS file to Virtuoso. So for that, importing the blank library should be created. For that, let us create one blank library with SCL180nm technology. Now go to File, Import, Stream. Now browse the GDS file. GDS file. Library, give the library which library you want to store. Untitled pad, I have created blank library. layout view, attach technology library here, give the layer map file. For layer map file, you have to go to SCL, this folder. Object is not required. More option. Give the reference library. Or you can select the manually the which library you are going to use. IFPad actually required, standard LEF is required, and this technology folder is also required. So I have given from this. Okay. Translate and translate. Zero error 20 warning. No need to check the log file. There is no error. So let's go to the library manager and go to orbital bed. So this layout view is there, and check if it's coming or not. Don't use schematic because there is no schematic of this. Okay. So this is the pad ring. You can see. Press Shift F to view the layers. So this is what I am talking about. I have generated the pad ring here, and now in this pad ring you have to put your layout and draw the layout diagram accordingly. So let us give the layout of inverter here, and let's check it. First of all, let's before acquiring, you have to verify which is the power pad and which is the ground pad. Everything should be identified. So for that, Control F and check the name. PB0A, PBDA. These are the IO pad power pad, and these are PB0I and PBDI is the power pad of the core circuit. So I have to make it sure that I have connected with this IO pad, the power rail. It is PDD and ground should be connected to this IO pad. So first of all, let's connect this one. Shift F. So here BSS is there. BSS is there. So take M3. Press R. Let's make the internal the inner ring as a ground. Now this is M3 and this is top metal, so I have to give one via M3 to top. So this is the bigger one, so it can increase the row, column, and give it here. So now the inner rail is connected to the BSS pad. This is BSS power pad. Next, you have to connect the VDD pad. So Control F, which one is VDD pad? This one, PBDI. So I have to connect this pad. Outer ring as VDD. So again connect the via. So I have connected the rail with my power pads. Now let us invoke our inverter event and check what we have made. Inverter layout here. But it's too small comparison to this. So let us keep it here. You can see here, this is the inverter. It's quite small in comparison to the IOPAD ring. So you have to zoom it in and out during our layout. So first of all, let us connect the VDD and power rails with the. For that, let us increase the width of this M1, then press O for M1, M2 wire. Then give M2. So inner one is the VDD ground, so outer one is my VDD. So connect it. Press O. M2, M3 wire it should be. M2 and M3. So give a bigger one. You can increase the size of the metal too. So I have connected the ground. Now I have connected the ground. So for that, similarly, I have to increase the size of the M1. M1, M2 wire is equal. And next, I require M2 to draw the remaining connections. Just stop here. Press O for wire M2, M3. 2, M3. Now take M3. So I connect to the ground. Now press M2, M3, M top layer. I have connected the power cord. I have connected. Now let us give the input output connections in and out. So for in, O, press O for via M1, M2, bias bigger one and reduce it. Still bigger. Now let us choose one IO pad. Here you can see one IO pad is there. You can use it. No, this is not. You cannot use this. This is a IO pad, ring power pad. So you can use this IO control. Let us check it. You can use these IOs. So upper one, which is nearer. So better to turn. Now here is a point. pad R point is there. So we have to take it this point with a metal tree and press S to test that gives it and the one pad is connected. Next another pad is there. Metal one is required for output pad. So here you can see the pad to take the metal to remove the wire. Select M2. Hit this M2. Okay. So this is the connection I have made. My tapeout for this inverter only I have finished. So after that I have to check the DRC LVS. For the tapeout, mainly DRC is taken into account because block level we have already done LVS packs. So for chip level, this die level only if you check the DRC and maintain the connection correctly, then it will be okay for you. But if you can do LVS analysis, that will be better. Full chip LVS analysis, if you can do, then it will be much more accurate. So for that, go to Calibre, run DRC. And DRC. It's big design, so big iPad several layers are there, so it's taking time. And iPad ring is several layers are there, so it's checking all the layers. After that, it's we are left with correcting the DDS file. So this may take lots of time for correcting the DRC because it's quite tedious job to finding each layer and do the DRC correctly, and then the DRC correctly. So up to this, I will be showing here. Rest I will be giving you the steps. You can proceed with the steps. to 41% is done. Now some error is there. I think that's why RV caliber RV is invoked. So one error is there, 13B1. In 13B1, it's showing M2 to M3 spacing. We add the metal width, so we have to check the M3 and M3 and M2 to M3 to M3 spacing. So it should be 0.28. So these are the errors. So we can minimize it by visiting the error. Check, click on this, press this highlighting button, go to the design. So I think in this area here, M3 to M3 spacing. So I think this layer is creating problem. So let us shrink this layer. So it's taking time. This layer, you have to make it correct. I think it is done. Check save. Next, again go to the highlighting number. Press this. This is also same. So let's check again. And these are the either 3R LT58, 3R LT20, 3R LT30, 6W, 9X, 11X. This will be corrected using dummy filling. So I am not showing here dummy filling. It will take some time. So due to time shortage, I am not showing you the dummy filling part. So after dummy filling, all the errors will be corrected. Only one error is to be corrected. That is 13B1. So I think it is corrected now. Let us check it. If persist, then we have to check it again, and we have to check it again. Run DRC again. It will take some time.
Yeah.
So,
Yeah, tell me.
so how to solve that property error in LBS?
Yeah, property error, you can solve it by editing the LBS rule file. Under the rule file, you just write unit length is equal to 1 micrometer.
Okay, length is equal to 1 micrometer in rule file.
Yeah, in rule file. After, or I will send you the rule file. You can change the. You can send me the mail ID. I will send you the corrected rule file. So it will be corrected.
Okay, sir. Okay, sir. Or how to stream out that GDS from Innovus?
Yeah, I will show you. Sorry, I'll show it.
Okay, sir. Okay.
So if there is any doubt, you can ask me by unmuting your mic. If there any question related, because it's taking time, so you can have some questions from your end, whether it is helpful or not. So these are the pad file IO pad I have used. You can see the document file given by the SCL. So there are lots of IOs. So you can also use it depending upon the necessity. By observing the datasheet, you can also use it. I think that either is connected because earlier 42% RV has invoked. So it's finished now. Survey. Yeah, these errors can be corrected using dummy fill. So you can ignore it for the time being. So this is all about the chip tapeout. And one student asked me to show the DDS file exporting from Innovas. So let's check it out. So this is the DDS design pirate pad. For exporting, go to file, save GDS. Here you can give the name, which if you can give another name also, you can give as according to your wish. Say suppose one, and map file should be given. So map file is this one, not layer map file. This TDS to FE foral map file should be given, which is supplied by the SCL. So you have to choose this map file. After that, apply. So you can find in this path on this pro1 is created here. You can see GDS file is extracted. This GDS file is imported in the Virtuoso as I have already shown. So I think it's clear. Ashima Gupta.
Yes, sir, it's clear.
So this is all about the tape out process. And let's go to the presentation again. So this is all about the demo of backend design. Next, I would like to introduce one topic that is algorithm to chip design process. How an algorithm and machine learning algorithm and any algorithm you can realize and you can make a full chip out of it. So for that, algorithm is written and simulated in with large dataset as the input in MATLAB. For designing any realizing any algorithm, you have to follow the MATLAB tool, and you have to write the m file coding in the MATLAB and run with a large dataset as an input and realize your machine learning algorithm or any clustering algorithm, whatever you are willing to design the chip. Then this algorithm, after designing or realizing in MATLAB, then VLSI architecture design along with design automation is done. This after getting an equation, this governing equation in algorithm, which is that is if you have some logarithmic function, if you get some square root function, if you get some other equation in the algorithm, then you have to generate or design this logarithmic circuit and adder circuit and subtractor circuit, anything if there is required. And then optimized architecture is written in Verilog. After that, you have to write this circuit in Verilog, right, means realize the circuit in Verilog, and behavioral simulation is done with the same dataset as input, which whatever you have given in the MATLAB, we have to give it in the behavioral simulation, and after that synthesis netlist with particular technology node is used as earlier we have done. And if any behavioral simulation, if any mismatch is obtained, then you can if there is a large error, then you have to optimize your architectural design. After that, if not, then go for post synthesis or LEC after generating the netlist, then timing analysis, then physical design is done in Cadence. Design verification is done using Caliber, and full chip tapeout is realized. That is, I have shown in the previous demo. And these are the some works we have designed, and that is cryptography algorithm we have realized in one chip using TSMC 180nm technology for IoT device. This is a lightweight block cipher design for resource constraint IoT device. Cryptographic algorithm is this chip is meant for only running this algorithm. Another thing is SVM support vector machine in machine learning algorithm is realized that it's hardware efficient VLSI design for cascade support vector machines with one chip training and classification capability is realized in using SCL using TSMC 60nm technology. So papers and links are available. You can check it for better knowledge. And our recent work, we have made one neural amplifier, pre-amplifier tapeout with a 2mm cross 2mm die. The process actually used one poly four metal process using SCL180nm technology. This chip is with us, and it is now in testing phase. And under the SMT CTST project. Another work is a low power high gain pre-amplifier for cochlear implants. That is, in cochlear implant, and generally we have to design one front-end amplifier or front-end part. So for that, we have to design one pre-amplifier. So we have designed a pre-amplifier, and this is the tapeout of this. It's still under process. It's also 2mm cross 2mm die size. And final conclusion. In conclusion, I will be giving you the rest of the steps which will be required for sending the DDS to file to the fabrication. After checking the DRC in chip, then you have to generate one dummy filling layer using the rule file. Dummy header file is there in the SLPDK. So you have to edit the dummy header file, giving the path of layout or the GDS file and the corresponding dummy GDS path. You have to give it, and after that, dummy GDS is generated, and that GDS is again imported in the Barchiso, and with after that this dummy field is imposed in the your chip tapeout design, and after that DRC is run. DRC is again run for getting any error or checking any errors. So after that, bond pad diagram is made from getting after getting the GDS file, bond pad GDS file from Foundry, and bond pad diagram is made. After that, final GDS file is exported, and this GDS file is sent to the Foundry for fabrication. So this is all about the chip tapeout process. And finally, acknowledgement, I should acknowledge MIT for supporting us with this industry-oriented tools, and SCL for giving us this their library and other technology files. Of course, VLSI lab infrastructure for ECE Department supported us giving all this high-end PCs and lab infrastructures. And these are our team members: Dr. Kal Vaishnav as chief investigator, Dr. Kaushik Go as co-chief investigator, and Mr. Anam Lashkar as a guest lecturer of the project, and Mr. Saurabh Chando as project assistant. These are our team members. Without the chief investigator and co-chief investigator, this another members, this chip tapeout would not be possible. They have guided us all in all aspects, and Mr. Anam Lashkar, guest lecturer, and Mr. Saurabh Chando has given their effort in front-end design and another theoretical analysis. So I am very much thankful to them for their support and designing this chip tapeout. So thank you all. Stay home, stay safe. So these are my contact details. You can contact me if any assistance required or any other queries. You can mail me directly and put your queries regarding your design. So over to
Thank you.
Bananis.
Thank you, Saurav sir. That was indeed a very informative session. Before concluding the session, I'd like to ask the audience if they have any questions.
So I think,
Hello.
yeah.
Sir, is there any equally good open source tool like Cadence?
No, actually, industry-oriented tool is not there. You can opt for a microwind. There is a software called microwind. You can do layout for only for study purpose, but not for a fabrication purpose. So, industry-related tool, Cadence, and Mentor, and Synopsys, these are used for fabrication or IC fabrication. So, if you require for fabrication, then it's not possible. But if you require for only for study purpose or for knowing the things, so you can opt for microwind software is there. So you can download it and run it.
Okay, sir.
Okay.
Hello.
Hello.
Sir, is it possible to get all the slides after the completion of the course?
Yeah, I will provide you all the things and after completion of course.
So after completion of the course, okay, with the permission from all the speakers,
Speakers.
okay, we will collect the slides and then we'll share. And also we'll share the recording also, because we are recording all the lectures, all the sessions. So obviously we will provide you the recorded version also. And this.
Thank you so much, sir.
Yes, sir. Sir, if the recordings will be shared, then it will be very beneficial for us.
Okay. So
Yes.
that's why. So it will actually need the permission from the speakers. If the speakers agree, then of course. Okay. Or I think the recording, maybe I think later on we have not decided, it will be uploaded in the YouTube, because we are having the official YouTube channel NIT Silchar is having. So we can upload it into the YouTube also, the recorded version, or also maybe the NIT Silchar website. From there itself you can download. Okay, so the information will be shared with you after the completion of the workshop.
So I think there is no question.
I think there is no question now.
So we can close it.
Yeah, can
Yes,
you
sir.
announce the tomorrow's schedule so that the participants get ready?
Yes,
tomorrow?
sir.
Yeah.
Yes, sir. Okay.
Yeah.
I'll be talking about the schedule for tomorrow. So day 2 we have from 9:30 we have Dr. Mustafizur Rahman from Intel USA. After that, the next session will be taken by Professor Sudeb Das Gupta, and then we'll take a recess, like lunch break from 1 to 2, and then again we will be having 2 sessions back to back. First will be taken by Professor Srinjoy Mitra, Edinburgh University, and the next will be by Dr. Bakul Gohel, who will be taking from DAIITC Ahmedabad.
Okay. So,
I would also like to request the participants to kindly fill up the feedback forms. The URL for the feedback form is provided in the chat box.
yeah. So before filling it, so I think you please read the instruction that is given carefully in the feedback form. So and then you correctly mention the speaker's name in the session wise, and then you fill up.
Okay, sir.
Yes, the session 2 speaker name is Mr. Saurabh Nath. Okay, due to the change in the schedule, the second session speaker name Mr. Saurabh Nath, and the session 1 speaker was Dr. KL Vaishnav, sir. Okay, and I request all the participants tomorrow you join early. I hopefully maybe 10 minutes back before the program will start, So we will try to start the program at 9:30 itself, and because you know this is the one guidelines for the OTOL and AICT guidelines. As per the guidelines, that 80% attendance is mandatory for awarding the certificate from AICT OTOL. So that's why. So please be present in all the sessions and enjoy the sessions. Interact with our speakers. Interact with the organizers. If you feel any kind of inconvenience or for any further informations, we'll be happy to provide you all the kind of facilities. So with this today, so I think we end this program, and thank you all for attending the today's program and making it a good interaction sessions today. And I hope that from tomorrow onwards also we will be attending all the sessions like the spirit of the today. So thank you all for bye bye for today.
Thank you, sir.
Yeah,
Thank
we'll
you, sir.
see you tomorrow morning.